All right, so now we take another step forward towards our final goal here. So 5 point, I think this is actually 3, yeah. 3, mutual inductance. Mutual inductance. So, taking this concept that we've just learned, magnetic flux changing through some loop, what if instead of the magnetic field that is, doing the fluxing with the loop, what if that magnetic field is not caused by a bar magnet? What if instead it's produced by another wire, right? So if you have a wire and you have current traveling in that direction, your right hand rule, as drawn up here, gives the direction of the B field. The B field wraps around the wire, like this. That is the magnetic field that is produced by current moving along that wire. So moving charge is what causes magnetic field, and we know pretty, conveniently how to move charge through wire. So what if our source of magnetic field was not a bar magnet, but instead a wire? And what if we bent this into a loop with some sort of potential difference on it, we'll say. I'd draw a little battery or something, but I want to keep it more abstract. So we'll just say A and B, and there's potential across A and B. And because there's charge moving through this, so let's say blue, or I was using pink before, so let's say that there's current moving. Let's see, which way do I want to do it? Yeah, current moving this way around this wire, as powered by some EMF source. It could be a battery, plug it into the wall, just don't think too hard about that. But we're driving current in this loop. And so because of that, if you use your right hand rule, just the same scenario as the induced current here, but in the other direction, your thumb points in the direction of the current, and the magnetic field is given by your fingers curling around. Oops. Like this, right? Like this. So if you notice, at every point that you do this exercise, it's always down the center of the loop. And that's no surprise, we were just talking about that before. And it may not be exactly straight down, but we'll just take it as being straight down. So the induced current, or the magnetic field that is caused by this current traveling around the loop, is down, which is pretty similar to this north end of a magnet, right? It actually would have that same splaying out kind of effect. I might as well draw it, I guess. It would look, something like this. It would look something like this, right? So that's pretty similar. Pretty similar to a north end of a bar magnet. If we were then to put our dummy loop, right, our loop with nothing attached to it, that's going to experience a wild ride here, nearby. And then we brought this thing closer, just the same as we did a bar magnet. But now we have it in a loop. Well, what if we didn't have to bring it closer, right? A bar magnet, static magnetic field, right? It has some set magnetic field according to its bulk properties and what have you. But how about this current-induced magnetic field? If you turn up the current, you've turned up the strength of the magnetic field. Turn down the current, you've turned down the strength of the magnetic field. So now we don't have to move it up and down. We don't have to move anything. We just have to adjust the current, and you get a change in magnetic flux. So I'm going to bring this guy closer, just so that it's more clear. Oops. So that it's more clear that there is magnetic flux from the other ring here, right? And what did I use? That greenish color. So there is magnetic flux through that ring caused by the flux, caused by the magnetic field of the top ring, right? So this is called mutual inductance, when you have two loops, one of which is powered and the other one is is experiencing a change in flux and then therefore an induced current, right? And it's going to be in the same scenario as up here, right? So if we go through this, boom, this is the current, because we want the induced magnetic field to be upwards to resist this change in flux. That is, if we were increasing, so increasing the current, increasing. If we were decreasing the current, then it would flip the other way, actually. All right, so here we have a circuit, super simple circuit, but it's just a circuit with not even a light bulb or anything onto it, just a loop of wire with current running around it, near another loop that is just a dummy loop with nothing on it, and we've induced a current on it. You're starting to put together how this wireless charging thing might work, I bet. So the EMF that's produced on each by the other, right? So if we were to switch which one's being powered, you get an EMF induced in the first by powering the second, or an EMF induced in the second by powering the first. And so the EMF that's produced in each of those scenarios by the other is equal to minus M, and I'll talk about what M is, delta I, and I'm going to write lowercase I because it's changing with time. So I'm going to change this here just to be consistent. I. So it's the same thing, it's current, but it's changing with time. So we'll write lowercase I of the first, that's a T. So the EMF here produced in the second loop is a function of the changing current in the first times this constant M, this proportionality factor M. And the EMF in the first, if we were to reverse this and control the current here and then induce something there on the first loop, would be negative M, just the same, delta I2 over delta T. Seems logical, but isn't it interesting that even if you flip them, then you get the same proportionality factor, M, right? And M is called the mutual inductance. So M equals mutual inductance. So given two loops, there is some mutual inductance factor, and that is equal to N2. I'll talk about what N is. Magnetic flux through 2 divided by the current of the first, and that is the same value as number of N1 magnetic flux through 1 and over the current 2. And N equals the number of turns in the coil. So instead of having one loop, you can have the effect amplified by having a coil, many turns. And so this number of turns, however many, is equal to N of that coil, right? So in our case, for a single loop, these would just be equal to 1, because the wire goes around one time. But you can amplify the effect, right, because it's in the numerator, you can amplify the effect by increasing the number of turns. So lowercase I is used to denote current that is varying in time. That's what produces the changing magnetic field in the first place, which then produces a changing flux through the other loop, which then induces the EMF, which is the whole point. So you have to have a changing current. And N1 and N2 refer to the number of turns in the first and the second circuit, respectively. And we usually refer to a circuit segment with multiple turns, multiple loops, as a coil. the SI unit of mutual inductance is equal to the Henry, or capital H, in honor of the American physicist Joseph Henry, who helped discover this effect. And 1 Henry is equal to 1 volt second per ampere, or equivalently 1 ohm second, or equivalently 1 joule per ampere squared, all those things. I know the units are getting a little wild and crazy, and at this stage my mind doesn't really make sense of these combinations of units, but they're useful when working problems, just to make sure if you get into a situation where the units are kind of weird, it's nice to be able to have different equivalent forms of all these units to make sure that have done your math correctly. So next we talk about self-inductance and inductors, and that's what all this is kind of building towards.